You know, modern AI search really does feel like magic. You type in a question, and boom, it pulls the perfect answer out of literally billions of documents. But what if that magic has a hard limit? Well, a new paper from Google DeepMind is suggesting that the very foundation of this technology has a mathematical ceiling we're about to hit. And frankly, it challenges some of the core assumptions we have about scaling AI.
Okay, so here's how we're going to break this down. First, we'll look at the incredible tech that makes AI search work. Then, we're going to peel back the curtain on this hidden mathematical limit the researchers uncovered. We'll see how they put their theory to the test, and you'll want to stick around for the shocking results. Finally, we'll explore what this all means for the future of finding information.
All right, first up, let's talk about the superpower behind pretty much everything, from your search engine to the shows recommended to you online. It's all built on one really powerful, unspoken assumption. At the very heart of this is a concept called vector embeddings. It's how we teach an AI to actually understand language. It takes any piece of text, whether it's your question or a whole document, and it turns it into a list of numbers, a vector. But this isn't just a random string of numbers. It's a coordinate in this massive meaning space where similar ideas are grouped close together. It's how a search for fast cars can find a document about high-performance automobiles, even if the words aren't exactly the same.
Now, this technology has been so wildly successful that it's led to this guiding philosophy in the entire AI community. If we just keep making our models bigger, feed them more and more data, and make our vectors longer, they'll just get better and better, eventually becoming perfect. The idea is that any problem can be solved if you just scale up.
But what if that core assumption is fundamentally flawed? This paper argues that, yeah, it is. It points to a mathematical limit that you can't just fix by making the models bigger.
The researchers at DeepMind asked this brilliant and almost deceptively simple question. Think about it. A search query has to be able to find any possible group of relevant documents from a huge library. Can one single vector, no matter how big and complex, really be flexible enough to represent every single possible set of answers you might need?
So you have this collision of ideas, right? On one side, you've got the industry's brute force method of bigger is always better. And on the other, you have this paper proving that the actual geometry of vector space itself puts a hard cap on performance, no matter how much data you throw at the problem.
Now, to prove this from a more academic angle, they framed the problem using something called a QREL matrix. Just think of it like a giant theoretical master answer key. It's a spreadsheet that has every possible question you could ever ask listed down the rows and every single document in the world across the columns. And in each cell, there's a 1 if the document is a correct answer for the query and a 0 if it's not.
And here is the absolute kicker from the paper. The dimension of your vector, basically how long that list of numbers is, directly limits how many unique sets of answers it can possibly point to in that master answer key. To get a bit technical, every retrieval problem has a certain complexity, which mathematicians call its sign rank. The dimension of your vector has to be higher than the problem's sign rank. If it's not, the vector physically doesn't have the capacity to represent every answer, and some questions become literally impossible to get right.
Now, what's so cool about this research is that they didn't just stop with the math. No, they designed these really clever experiments to see if this mathematical ceiling actually shows up, both in a perfect, simulated world and in the messy reality of natural language. So first, they went into the lab. They created this ideal, best-case scenario simulation. They didn't even use language. They just optimized the vectors themselves. And the results? Crystal clear. They found this very distinct breaking point, where adding more documents just overwhelmed a vector of a certain size. It proved the theory in a perfect environment. To handle more possible answers, you absolutely need more dimensions.
This is where their next move comes in, and it's brilliant. They built a real-world data set they called Limit. The task seems almost trivially simple. A query is like, who likes quokkas? And a document is like, John Durbin likes quokkas and apples. But here's the genius of it. It's built specifically to force the model to handle a massive number of different combinations of answers, targeting that exact theoretical weakness we just talked about.
Okay, so they've got their theory, they've built their stress test, and now it's time to unleash it on some of the most powerful, state-of-the-art models in the world. This is where things get really dramatic.
So, you have to wonder, right? Could these massive billion-dollar models, trained on pretty much the entire internet, just muscle their way through a problem that's designed to be their kryptonite?
The results were, honestly, they were staggering. They failed. And I mean, they failed badly.
These top-tier models struggle to find the correct two documents, often scoring below 20% on recall. That means they found less than 1 out of 5 correct answers, even when we gave them 100 guesses. They just couldn't represent all the combinations.
And the researchers themselves, they don't mince words. They state it right in the paper. Models severely struggle, even though the task is trivially simple. This just shows this huge disconnect between how smart we think these models are and what their actual representational power is when you push them in just the right way.
I mean, this chart says it all. On the left, you've got Gemini Embed, a state-of-the-art dense model. It scores a measly 10%. On the right, you've got BM25, a much older sparse model, where most of the vector's dimensions are just 0. Because these sparse models act like they have almost infinite dimensionality, they completely sidestep this particular problem and score over 93%. It proves it's not about the model being smarter, it's about having the right mathematical bones for the job.
So if the main highway we've all been driving on is headed for a mathematical dead end, what are the other routes? Well, the paper doesn't just leave us with the problem, it also points towards some solutions.
Turns out there are other ways to build these systems. You've got things like cross-encoders, which are way too slow for the initial search but don't have this dimensional limit. Then there are multi-vector models like Colbert, which use lots of vectors for each document, making them way more expressive. And, as we just saw, the old-school sparse models naturally have the high dimensionality to just breeze past this issue. So the big takeaway here is that we can't just keep making our current models bigger and bigger and expect them to solve everything. We've hit a theoretical wall. The future of AI search that can actually follow complex instructions is probably going to require us to move beyond this single vector idea and embrace these more expressive and, yeah, maybe more complicated architectures.
And that leaves us with this really provocative final thought. This research brilliantly uncovered one fundamental limit that was hiding in plain sight this whole time. So it forces you to ask, what other assumptions are we making? What other mathematical ceilings are we speeding towards without even knowing it?